So as we start to get into chapter 3, we're getting into a lot more math. You guys had some math exposure with dimensional analysis in chapter 1 and some conversions, molar mass, mole conversions, etc. in chapter 2. But now is where we're really going to start hitting the math a lot harder, and it continues, to be honest, through chapter 8 is a lot of math, and then 9 through about 12 are more conceptual. So we're going to really start hitting the math hard. If you're having a hard time with the algebra, please come ask for help during office hours so we can get you comfortable, because we're adding concepts and math now, and it can kind of bog some students down. First example, a metal representing by the letter M, so we're going to say letter M, forms an oxide with the formula M2O. Again, oxide means oxygen, okay? Oxide is the ion of oxygen, or the anion specifically. If the oxide, that's what we would call the compound, contains 16.99% oxygen by mass, what is the identity of the metal? So the way to approach this question is kind of think about what it's telling us. It's telling us we're forming some compound with the form M2O. What does M2O tell me? Well, first, I know that oxygen can only be -2, right? If I form oxide, oxide means O2 minus. So this means that the metal must have a +1 charge. That narrows it down some. Some metals don't have a +1 charge. Now, it doesn't narrow it down completely. It does tell me that it's either an alkaline metal or a transition metal that has a +1 oxidation state. And I know that you guys don't have all the transition metals memorized. I don't either. I mean, I have their names memorized, but not like all their oxidation states. But it does narrow it down a little bit. Like it tells us it can't be an alkaline earth metal. It's not going to be aluminum. It's not going to be zinc. Like that kind of stuff I know already. So how am I going to go ahead about solving this? Well, let's think about this. I'm going to say I want to find, when we don't know what else to do, first thing I want to do always is find the number of moles I have of the species. It only tells me the percent oxygen by mass. It doesn't tell me anything about the other species, but it does tell me percent oxygen. So I'm going to go ahead and find the number of moles of oxygen I have. I have 16.99 grams of oxygen. How do I have 16.99? Because remember, we're going to assume 100 gram sample. If I assume a 100 gram sample, that means I would have 16.9 grams of oxygen in my sample. Convert that to moles. 1 mole of oxygen to 16 grams of oxygen gives me 1.06 moles of oxygen. How does that help me? Well, by law of multiple proportions, I know that because I have 0.106 moles of oxygen, I must have 2.12 moles of my metal species, M+, because remember it's going to be a +1 charge. Cool, so I know the moles of each one, but that still doesn't tell me the identity of the metal, right? But I assume I have 100 grams of sample. So how does that help me? This is where you have to kind of think about what the definitions mean in the different things we're doing. If I have 100 gram sample, and I know 16.99 grams of that is due to oxygen, that means 83.01 grams is due to my metal. Now, and this is where I'm going to lose some of you, so please come ask if you're confused by this. I've got grams. I've got the number of moles I have for the same species. So again, 100 gram sample, I have 16.99 grams of oxygen, I have 83.01 grams of my metal, because law of conservation of mass is got to be composed of the whole thing, right? The entire compound is just M2O. So if I have 100 gram sample, I know 16.99 grams of that sample are due to oxygen, therefore 83.01 grams of that sample are due to M+. I found the moles of oxygen I have, and I found that I had 1.06 moles of oxygen. If I have 1.06 moles of oxygen, I must have 2.12 moles of M2. Law of fixed and law of multiple proportions tells me that. It's in a set order. What I'm going to do now is use a definition. Molar mass. Molar mass is equal to the number of grams of your sample, whatever species you're looking at, divided by the number of moles of that sample. I have both of those pieces of information. My number of grams I found to be 83.01 grams. My number of moles we found to be 2.12. If I divide grams per mole, that gives me 39.1 grams per mole, which matches to the table and tells me it's potassium. Potassium is an alkaline metal. Alkaline metals have a +1 charge, so it matches the formula perfectly. So this will be K2O. And again, your metal is potassium. So if you were to get a question like this, you would have to show all this math to prove this. You can't just give the answer. You have to prove how do you know that's the answer. An unknown compound contains the following percentages by mass. Carbon, 68.06%, hydrogen, 5.83%, oxygen, 23.16%, and nitrogen, 10.14%. Find your empirical formula. What is empirical formula? Empirical formula is your lowest whole number, mole-to-mole ratio. So I'm looking for lowest numbers, whole numbers, and mole-to-mole ratio. Hopefully that helps remind you that the first thing you need to do is calculate moles. So first we're going to find the number of moles of carbon just so it's listed first. The other thing to remember here, and I always forget to write this down, you do not need to write this down, but you need to do it because it makes it easier. Assume you have a 100-gram sample. If you have a 100-gram sample, then your 68.86% becomes 68.86 grams. I should say number of moles of carbon, 60.86 grams of carbon. Convert that to moles of carbon. And I find that gives me 5.07 moles of carbon. I'm going to do the same thing for hydrogen, oxygen, and nitrogen. So number of moles of hydrogen, 5.83 grams of hydrogen. 1 mole of hydrogen is 1.008 grams of hydrogen. Oops. This gives me 5.78 moles of hydrogen. Oxygen, number of moles of oxygen, 23.16 grams. Convert to moles of oxygen. Gives me 1.45 moles of oxygen. And last but not least, nitrogen. Number of moles of nitrogen. I'm given 10.14 grams of nitrogen. 1 mole of nitrogen is 14.01 grams. And this gives me 0.724. I'm going to divide all of the numbers by the smallest number. So I'm going to divide this by 0.724. So again, because we want a whole number ratio. So we've got moles. Now we want to find the mole-to-mole ratio. But we want it to be the lowest and whole number. So what I'm going to do is I'm going to find the lowest number and I'm going to divide by that lowest number. So I'm going to divide all of them by 0.724. And when I get a not whole number, I'm going to round to a whole number. What this does is this tells me the relationship of the species to each other. This tells me that I have 7 carbons to every 8 hydrogens to every 2 oxygens to every 1 nitrogen. And of course, we don't have to write the 1 below the nitrogen, so I wrote it there temporarily to show you, but we will erase that. And this is my empirical formula. You need to be comfortable doing empirical formula calculations because they come back even in second semester chemistry. I recently gave one to my second semester kids, and out of the whole classroom, there was only a small handful that remembered how to do empirical formula, and only one of them that did it perfectly, because students like to kind of brain dump, and this is not something you can brain dump. Empirical formula comes back throughout chemistry. Okay, a 0.3427 gram sample of Bronze Age jewelry is analyzed for silver content by first dissolving it in nitric acid and precipitating it as silver chloride. The precipitate is transferred to a dry, sinistered glass filter weighing 12.2347 grams, where it is separated from the filtrate and washed with dilute nitric acid. The filter and precipitate are dried at 150 degrees C, cooled, weighed, and found to weigh 12.4373 grams. Calculate the percent silver in the jewelry. So, 0.3427 gram sample. We're analyzing for silver. We're precipitating out silver chloride. The precipitate is transferred to a dry, sinister glass filter weighing 12.2347 grams. The filter and precipitate are dried at 150 degrees C, cooled, weighed, and found to weigh 12.473 grams. Calculate percent silver. This is a gravimetric analysis problem. What I want to know is, so basically I've got this sample, so I've got this not fancy piece of jewelry that weighs 0.3427 grams. I'm going to take this sample and I'm going to put it in a beaker with nitric acid. What's going to happen is it's going to completely dissolve that sample of jewelry. And there's going to be silver ions that are going to float around from the jewelry itself. It's going to release everything, but the silver ions will float around. To this, some type of chloride solution is added. Nitric acid does not have chloride, but some type of chloride solution is added, whether that be, sodium chloride or something. I add some type of chloride here. Let's say we add sodium chloride. When I add sodium chloride, what happens is the sodium ions break apart from the chloride ions. And we will talk more about this in chapter 5. But these start floating around in solution because sodium chloride is an electrolyte and is soluble. Silver chloride is not soluble. So the silver and chloride ions find each other and they're going to precipitate out. And I know these pictures are getting worse and worse. I'm sorry. It's going to precipitate out. It's a solid in the bottom. And then in solution, will still be floating around your sodium, your nitric acid. Oops, that should be a negative sign there on your nitrate. It's trying to write H+, etc. But this solid down here will be silver chloride. That silver chloride solid will be isolated from the system and dried and then washed with dilute nitric acid to remove any impurities, filtered, weighed, etc. And then from there we can determine the percent silver that's in the jewelry, because all of the silver in this jewelry, so all the silver up here, would have been reacted with chloride ions and formed this solid. We want to know how much was in the original jewelry. So we know our mass of our sample. (0.3427 grams). We know that the sample was cooled, weighed, and found to weigh 12.4373 grams. And we know that when the precipitate was transferred to a dry sinister glass filter, it weighed 12.2347 grams. So the mass of silver chloride itself is the difference between those, 12.4373 grams minus 12.2347 grams. Why the difference here? Because again, this 12.2347 is just your glass filter. This, where is it? Sorry, 12.4373 grams here. This is your filter plus sample. Or your silver chloride. This here is just your filter. It's just saying dry sintered glass filter, being just specifying the fact that the filter itself is dried, so it's not adding water weight to your system. This equals 0.2026 grams of silver chloride that was actually isolated. I need to know the number of grams of silver so I can compare that to the original sample. Number of grams of silver, 0.2026 grams. Silver chloride. I'm mixing up silver and chloride here. Silver chloride. Convert that to moles of silver chloride. Now, I know that I have 1 mole of silver for every 1 mole of silver chloride. Now that I have moles of silver, and this is silver ion technically, I know that I can convert that right over to grams of silver. 107.9 grams of silver to 1 mole of silver. And this is 0.1524 grams of silver. Now technically it is silver ion, but a silver ion and a silver atom are going to weigh basically the same because losing 1 electron, the electrons are so small they're not really adding weight to your overall system. Now that I have my grams of silver, I can say my percent of silver in the sample. This will be the mass of silver divided by your mass of sample. .1524 grams of silver per 0.3427 grams of sample times 100% gives you 44.47% silver. Now I didn't show it here, but I could do right here, I could do one more conversion that just shows 1 mole of silver for every 1 mole of silver ion. I'm not worried if you show that or not. It's basically this, at this point, it's the same thing because it's a 1-to-1 relationship. But the important part here is what we're trying to find. Sorry, I was trying to highlight the different color. 44.47% of that jewelry sample is actually comprised of silver. Okay, you are given a 0.456 gram sample of a mixture of NaCl and FeNO3. You add water to dissolve the solid completely. Next, you add NaOH, which reacts with the iron 3 cations to form the insoluble precipitate FeO3. The solid is filtered, dried, and massed, and it's found to be 0.107 grams. Calculate the percent iron by mass in the mixture. So, 0.456 gram sample, mixture of sodium chloride and FeNO3. Insoluble precipitate, iron 3 oxide or iron 3 hydroxide is formed. We isolate 0.107 grams, and we want to know percent iron by mass. Again, this is gravimetric analysis. So, what's actually happening here, we're adding FeNO3, 3, so iron 3 nitrate is being mixed with sodium chloride. Oops, not writing straight at all, and it drives me nuts. It's mixed with sodium chloride and NaOH. So this was the original mixture, and we add water to dissolve this completely, then I add the sodium chloride. So I've got some kind of beaker or some kind of flask, some kind of system. I've added the solid of FeNO3 and NaCl in water. What that does is it gives me Fe3 plus ions, 3 NO3 minus ions, Na plus ions, and Cl minus ions. And these are all just floating around in solution, okay? To this, I'm going to add NaOH. What that does is it creates more sodium ions in solution and hydroxide ions in solution. And you guys don't know this part yet, but we'll know it soon. Iron hydroxide, iron 3 hydroxide specifically, is insoluble, and so the iron's going to find 3 hydroxides and it's going to crash out and form the solid in the bottom of the beaker. The sodium ions and the nitrate ions and the chloride ions are going to continue floating around. But adding that hydroxide to it is what's going to cause that iron 3 hydroxide to crash out. So this will give you iron 3 hydroxide. You need 3 sodium hydroxides to every 1 iron. We're going to learn balancing in the very next chapter. And we also have the NaCl that's just a spectator hanging out. The NaCl doesn't do anything. Now, I know that my NaCl plus my FeNO3, 3, or easier to say iron 3 nitrate, equals 0.456 grams. I know that my iron 3 hydroxide equals 0.107 grams. I want to know percent iron by mass. So I need to find the number of grams of iron in my sample. I have 0.107 grams of iron 3 hydroxide. Convert that to moles of iron 3 hydroxide. Now that I've got moles of iron 3 hydroxide, I'm going to convert to moles of iron. I know there's 1 mole of iron for every 1 mole of iron 3 hydroxide. Now that I've got that, I can easily convert over to grams of iron. I've got 55.85 grams of iron to every 1 mole of iron. This gives me 0.0559 grams of iron. So I can easily find the percent iron in the sample, 0.0559 grams of iron, 0.456 grams total sample, times 100% gives me 12.3% iron in my final sample, in my original sample. So if I had 0.456 gram sample and had a mixture of sodium chloride and iron 3 nitrate, I dissolved that sample in water completely, added hydroxide. The iron 3 cations react to form insoluble precipitate iron 3 hydroxide. I collect that solid, I filter it, dry it, and I weigh it, and I find it to weigh 0.107 grams. That means that this original sample here contained 12.3% iron. Okay, cisplatin is the common name for a platinum compound that is used to treat cancerous tumors. It has the mass composition of 65.02% platinum, 9.34% nitrogen, 2.02% hydrogen, and 23.63% chlorine. I want you to calculate the empirical formula for cisplatin. So again, as a reminder, empirical formula is the lowest whole number multimole ratio. Because we're given just pure percentages, we are going to assume a 100-gram sample. Again, you do not need to write this assumption on your work. I'm just reiterate this because I know it can help students kind of remember when you're doing these problems how to go about it. So first, let's find the number of moles of platinum. 65.02% would be 65.02 grams. Convert that to moles of platinum. 1 mole of platinum is 195.08 grams. It's one of your transition metals, and it's a little lower on the table, so it's a little bit larger mass. This equals out to 0.3333 moles of platinum. Next, number of moles of nitrogen. 9.34 grams of nitrogen, because 9.34% convert to grams. Convert that to moles of nitrogen. 1 mole of nitrogen is 14.01 grams of nitrogen. As another reminder, I know we learned about diatomics in this chapter. When we're dealing with empirical formula here, and I say nitrogen here, this actually means just nitrogen, not N2. Hydrogen here means just H, not H2. Chlorine here means just Cl, not Cl2, because it's a multiple ratio of the elements to other elements, not the overall intended formula. This gives me 0.6666 moles of nitrogen. Number of moles of hydrogen, 2.02% is 2.02 grams. 1 mole of hydrogen equals 1.008 grams of hydrogen. And this is going to give me 2.004 moles of hydrogen. And last but not least, number of moles of chlorine. 23.63% is 23.63 grams. 1 mole of chlorine weighs 35.45 grams. This gives me 0.6666 moles of chlorine. Next, we've got the moles. Now we want to find the multiple ratio. To do this, we also want the lowest and we want whole numbers. I want you to go through and find the smallest number of moles you have and divide all of your values by that smallest number. So we're going to divide everything by 0.3333 moles. This gives me 1 mole of platinum, or 1 platinum because units cancel, divided by 0.3333 moles. Gives me 2 nitrogens, divided by 0.3333 moles, gives me 6 hydrogens, and divided by 0.3333 moles, gives me 2 chlorines. This means overall, I have 1 platinum, 2 nitrogens, 6 hydrogens, and 2 chlorines for the overall empirical formula of this compound. So you do still have to do all the work to show everything, but this is how the final answer is this answer. All of the work counts for full credit though. But if you're looking for just the empirical formula, what's highlighted is your actual answer. Okay. When a 0.3546 gram sample of vanadium metal is heated in air, it reacts with oxygen to achieve a final mass of 0.6330 grams. Calculate the empirical formula of this vanadium oxide. I know vanadium is V. It's going to react with oxygen to form vanadium oxide. So I want to figure out the formula. So VXOY, where X and Y represent the individual numbers I have for one species to the other. I do know oxygen is 2-, but I have no idea what charge vanadium would be. So vanadium I have to calculate, oxygen I know will be -2. Basically, I have so many moles of vanadium reacting with so many moles of O2 to form this VXOY compound. And I'm not sure what that will be. So let's go ahead and think about what we've got here. Let me highlight what's important. 0.3456 gram sample of vanadium metal. Heated in air, reacts with some unspecified amount of oxygen and gets a final mass of 0.6330 grams. Well, I do know the number of grams of vanadium I have, so I can go ahead and calculate my moles of vanadium. So let's go ahead and do that. Number of moles of vanadium, 0.3546. I keep saying this backwards. I apologize. 3546 gram of vanadium. Convert that to moles of vanadium. Vanadium has a molar mass, or atomic mass rather, 50.94 grams. This gives me 0.00696 moles of vanadium. Now, how do I know how much oxygen I have? I need to find the moles of oxygen so I can find the empirical formula. Well, I know that if I burn this vanadium in the presence of oxygen, its final mass is 0.6330 grams. I know by conservation of mass, matter cannot be created nor destroyed. Therefore, the difference in the mass here must be the mass of oxygen. So 0.6330 grams minus 0.3546 grams. Overall, I have 0.2784 grams of oxygen in my final compound that I've made. So with that, I can find the number of moles of oxygen. Again, O here, not O2, because that's the relationship of them to each other in a compound. We're not talking about oxygen. Like oxygen reacted, yes, we're talking about in an overall compound, what compound did we form? 0.2784 grams of oxygen. Convert that to moles of oxygen. Equals 0.0174 moles of oxygen. So 0.00696 and 0.0174. This is clearly my smaller number, so I'm going to divide both numbers by this. I get 1 and I get 2.5. I need my lowest whole number. I promised you guys would not have to round at 2.5, and that is true. Instead, you need to multiply. You need to multiply this number by some whole number to make everything a whole number in the lowest ratio. I'm going to go ahead and multiply both of these by 2. This gives me 2 vanadiums to 5 oxygen. So I did promise you would not have to round to 2.5. That is true. You will have to multiply. So 2.5 times 2 gives me 5. The overall empirical formula here is V2O5. A 1 gram sample of an alkaline earth metal chloride is treated with excess silver nitrate. All of the chlorides are recovered as 1.38 grams of silver chloride. Identify the metal. 1 gram sample. We know it's an alkaline earth metal chloride. We're adding excess silver nitrate. The chloride ions recovered as 1.35 grams of silver chloride, and I want to know the metal. Alkaline earth means group 2, which all have +2 charge, which means I have some formula of MCl2. I know that the chloride reacts with silver to form insoluble silver chloride. That's why I added the excess silver nitrate here. So I want to find the number of moles of chloride I have, or number of grams of chloride I have in my original sample. If I can find the number of grams of chloride, I can subtract that from here, and then I can find the grams of unknown I have. So let's first get the number of grams of chloride. 1.38 grams of silver chloride are isolated. Convert that to moles of silver chloride. I know that there's 1 mole of chloride ion to every 1 mole of silver chloride. If you want to, you can even say, 1 mole Cl to 1 mole of Cl minus. That's fine. I don't care if you don't include this step. Times 35.45 grams of chlorine to 1 mole of chlorine. 0.341 grams of chlorine. The entire sample weighed 1 gram. So 1 gram minus 0.341 grams from the chlorine tells me I have 0.659 grams of unknown metal. Again, the unknown metal is an alkaline earth, so the formula of the compound has to be MCl2. I want to know the number of moles of metal I have. I know I have 0.341 grams of chloride. Convert that to moles of chloride. Now I can convert that to moles of metal. I know I have 1 mole of that metal unknown to every 2 moles of chloride in the sample because it's MCl2. 1 metal, 2 chlorides. This gives me 0.00481 moles of your metal. Now I have grams of my metal, moles of my metal. So I can do what I like to do and solve for molar mass. Number of grams of metal divided by number of moles of metal. 0.659 grams of your metal divided by 0.00481 moles of your metal. Gives me 137 grams per mole. Now look at the periodic table. What alkaline earth metal has a molar mass of about 137 grams per mole? It is barium. So the answer to this whole question is barium. Calculate the empirical formula, so we're going to do empirical formula now, for the stimulant listed based on elemental mass percent composition caffeine. So, empirical formula for caffeine. We have percentages here, so we're going to assume 100 gram sample. Number of grams of carbon, 49.48 grams carbon. Convert to moles of carbon. Gives me 4.120 moles of carbon. That should say number of moles up here. I apologize. I was thinking about what I was writing next, not what I was looking for. Next, number of moles of hydrogen. 5.19 grams of hydrogen. 1 mole of hydrogen to 1.008 grams of hydrogen. Gives me 5.15 moles of hydrogen. Number of moles of nitrogen, 28.85 grams of nitrogen. 1 mole of nitrogen weighs 14.01 grams of nitrogen. 2.06 moles of nitrogen. And number of moles of oxygen. 16.48 grams of oxygen. 1 mole of oxygen to 16 grams of oxygen gives me 1.03 moles of oxygen. Find the smallest number and divide all of them by that smallest value. This gives me 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen. So the final formula, the empirical formula for caffeine, C4H5N2O. Number 9, a chemist decomposed the following sample. Determine the empirical formula of each. I don't know why I said of each. Just determine the empirical formula and ignore the fact that it says of each, because it's one compound. So I've got 2.67 grams of barium and 3.115 grams of bromine. Here we don't have percentages or anything, but that actually makes it easier. Now I can just go ahead and convert right to moles. I don't even have to worry about making any assumptions. Number of moles of barium, 2.677 grams of barium. 1 mole of barium weighs 137.3 grams. This gives me 0.01950 moles of barium. Number of moles of bromine, 3.115 grams bromine. 1 mole of bromine weighs 79.90 grams. This gives me 0.03899 moles of bromine. I see this as my smaller of the two numbers, so I'm going to divide both by that number. So I've got 1 barium to 2 bromine, which makes sense. Barium's 2 plus, bromine's 1 minus. I expect it to be this formula, BaBr2, and if I asked you to name it, it would be barium bromide. Because it's an ionic compound, metal and nonmetal, and since barium is an alkaline earth metal, it has a fixed oxidation state, so I don't have to specify it during or in the naming itself. I can just say barium bromide. Forgot to highlight that one. What is the empirical formula? That should say formula. I do really well when I write these things, apparently. I swear I spell check, but spell check didn't pick that up. What is the empirical formula? So I'm looking for empirical formula for isopropyl alcohol, which contains only carbons, hydrogens, and oxygens. If the combustion of a 0.25 gram sample of isopropanol produced 0.561 grams of CO2 and 0.306 grams of water. Remember what combustion is. Combustion is when I take a compound, so in this case I'm taking a carbon, hydrogen, oxygen compound, and I don't know this formula. So CXOY, you can write this in any order, but I usually write CHO. So CXHYOZ, gotta determine what X, Y, and Z is, reacts with oxygen to form CO2 and water. That is your combustion reaction. all of the CO2 produced comes from the reaction of this carbon with the oxygen in your sample. So all the carbon here goes into producing this CO2. Again, the oxygen can come from multiple sources. Water here, all of that hydrogen comes from the hydrogen in the original sample. Water can come from both spots, but all the hydrogen goes into producing water. So first, I want to find the number of moles of carbon. But to do that, I'm going to use the amount of CO2 I have to determine how much carbon went into making that much CO2. So I have 0.561 grams of CO2. Convert that to moles of CO2. I know there's 1 mole of carbon for every 1 mole of CO2. This gives me 0.0127 moles of carbon. I'm going to do a similar process for hydrogen. Number of moles of hydrogen. I have 0.306 grams of water. Convert that to moles of water. And I know I have 2 moles of water for every 1 mole of H2O. This gives me 0.0340 moles of hydrogen. Now, for combustion, the trick is remembering that the mass of the entire sample is due to the mass of carbon plus the mass of oxygen plus the mass of hydrogen. And I know my entire sample weighed 0.255 grams. I have the moles of carbon and I have the moles of hydrogen. I can find the mass of carbon and hydrogen from this information and use that to find the mass of oxygen in the original sample. So I'm going to convert this to grams of carbon, 0.153 grams of carbon. I stopped here because I do need the number of moles as well. That's why I didn't continue the calculation just entirely before. So I know I have 0.153 grams of carbon and 0.0342 grams of hydrogen in my original sample. So the number of grams of oxygen I have a 0.255 gram sample. I subtract out the amount of carbon, 0.153 grams due to carbon, and the amount from hydrogen, 0.0342 grams of hydrogen, and I get the mass of just oxygen. I find that it's 0.0678 grams of just oxygen. I use that information to find the number of moles of oxygen. So 0.0678 grams of oxygen. Convert that to moles of oxygen. Gives me 0.00424 moles of oxygen. Now I'm going to run out of space here, and so I'm going to shrink all this down because I don't want to erase it on the problem if I don't have to. And put that up there. But now I have moles of carbon, moles of hydrogen, and moles of oxygen. Now I can go ahead and do the mole ratio portion of the empirical formula calculation to find the overall formula. So for carbon, I have 0.0127 moles of carbon. Hydrogen, I have 0.0340 moles of hydrogen. And oxygen, I have 0.00424 moles of oxygen. Obviously, the number for oxygen is a small, so I'm going to divide all of them by that number. So divided by 0.00424 gives me 3 moles of carbon. Divided by 0.00424 moles gives me 8 hydrogen. Divided by 0.00424 gives me 1 oxygen. So my overall empirical formula, C3H8O. Combustion reactions are a little more difficult because you have to remember all of the CO2, all of the carbon in the CO2 comes from your original sample. You can have all kinds of things in here, but this sample had carbon, hydrogen, oxygen. But all of the CO2 came from this. All of the carbon in the CO2, I mean. Oxygen came from multiple sources, and all of the hydrogen came from here as well. So if we can find those first, we can back calculate to figure out how much oxygen actually reacted. Since oxygen is its own reactant, and in the original reactant, the hydrocarbon itself, or the carbon, hydrogen, oxygen, it's in the isopropanol itself, it's more difficult to figure out how much oxygen I have. So if I can instead figure out how much did my final sample weigh, how much was my original sample, I can back calculate to figure out how much oxygen actually reacted. Because oxygen's in excess, otherwise I can't determine how much oxygen I actually started with. Example, write the formula of the following acids. You just need to know acids. Hydroiodic acid. Iodo. Iodo is telling me iodine. Sorry, my brain completely just spaced out entirely there. I've got hydro in front and ic, which means it came from iodide. Iodide is I minus, and I added enough protons to it to make it neutral, which means H plus. So hydroiodic acid, HI. Nitrous acid, OUS. We add OUS if we started with ite. That means I started with nitrite. Nitrite is NO2 minus. I had to add enough protons to it to make it neutral, which means I have HNO2. Sulfuric acid. Ic, no hydro in front, just ic, comes from 8. That means I had sulfate. Sulfate, SO4 2 minus, so I need 2 protons to make this neutral. H2, SO4. Hydrosulfuric acid. I've got the sulfur in the center here, but I've got hydro and ic. That means that it came from sulfide, which is S2 minus, and I needed 2 protons to make that neutral, so H2S. Nitric acid, no hydro in front, tells me that it came from nitrate, which is NO3 minus, so I needed 1 H plus to make this neutral, HNO3. Acetic acid. Ic again tells me it came from 8, so acetate, which is CH3COO minus, or again, you guys are welcome to write it as C2H3O2 minus. I don't care. I just have a harder time writing it that way. But I will recognize it and give you credit. You need 1 H plus for this. So this one we most often will write as CH3COOH. Usually put the H at the end here. You could also write the C2H3O2H is often common to see. You could do C2H4 O2. This one's going to take me a little longer to recognize, so I don't recommend writing that one. I recommend putting the H on the end so I actually recognize it. But anyway, that's acetic acid. That's what makes vinegar smell so bad. And carbonic acid. Ic means it came from 8. So carbon 8, CO3 2 minus. I need 2 protons to neutralize this, or to make this a neutral compound. H2, CO3. And that's what eventually leads to the bubbles in your drinks. Let's do another combustion example. Combustion of 30.42 grams of a compound containing only carbon, hydrogen, and oxygen produces 35.21 grams of CO2 and 14.42 grams of H2O. What is the empirical formula of this compound? If the molar mass of this compound were 228.156, that should say grams per mole after it, what would be the molecular formula? Well, let's see what's important. We combusted 30.42 grams of a sample that contains only carbons, hydrogens, and oxygens. It produces 35.21 grams of CO2 and 14.42 grams of H2O. I want to know the empirical formula. Then, if molar mass is 228.156 grams, I want to know molecular formula as well. So first, again, we know that all of the carbon in the CO2 came from carbon in the original sample. So I've got CXHYOZ reacting with O2 to form CO2 and water. I don't know how much oxygen I have because it's coming from multiple places and because this is an excess. But I know that all of my carbon went into forming CO2. So I can use that information to find the number of moles of carbon in my original sample. I produce 35.21 grams of CO2. Convert that to moles of CO2. I know that I have 1 mole of carbon for every 1 mole of CO2. This gives me 0.8000 moles of carbon. Same thing for hydrogen. I know all of my hydrogen went into making water. I have 14.42 grams of water. Convert that to moles of water. I know there's 2 moles of hydrogen for every 1 mole of H2O. This gives me 1.600 moles of hydrogen. Now, again, I don't know how much oxygen I have, but I do know that my original sample was comprised of carbon, hydrogen, and oxygen only. So if I can find the number of grams of carbon and hydrogen I have, I can back calculate to find the number of grams of oxygen I have. So I'm going to use this to find the number of grams of carbon. I have 9.609 grams of carbon in my original sample. And hydrogen, I have 1.613 grams of hydrogen in my original sample. So to find number of grams of oxygen, I know I have a 30.42 gram sample. I'm going to subtract out 9.609 grams of carbon and 1.613 grams of hydrogen, and I find that I have 19.198, sig figs are here, grams of oxygen. Now I can find my number of moles of oxygen. So my number of moles of oxygen, 19.198 I'm just underlining where my sig figs are. Gives me 1.200 moles of oxygen. Now, like last time, I need to shrink this down because there's no way I can keep writing on this slide. So I'm going to shrink this down and put them right there. Now, to find the empirical formula, I need to divide all of them by the lowest number. I have 0.9609, 1.613, or 1.2. Oh, sorry, I just underlined the right numbers. Those are grams. That makes more sense. 0.8000 moles, 1.6 moles, or 1.2 moles. Those numbers make a lot more sense to me. So for carbon, so let's label this. We're going to do empirical formula. For carbon, I have 0.800 moles of carbon. Hydrogen, we found it to be 1.600 moles. Oxygen, I found to be 1.200 moles. When I compare these numbers, I see that the moles of carbon are the smallest number. So I'm going to divide everything by 0.8000. That gives me 1 for carbon, 2 for hydrogen, and 1.5 for oxygen. Now, I promised you guys I would not make you round at 1.5, and that is completely true. But that doesn't mean you don't have to multiply. We do have to multiply this one. This number looks great. This number looks great. But this number does not look great. I need to multiply all my values by 2 to get my empirical formula. It is the lowest whole number mole to mole ratio. So times 2 gives me 2 carbons, times 2 gives me 2 hydrogens, times 2 gives me 3 oxygens. My overall empirical formula, C2H4O3. This is an empirical formula. It is my lowest whole number mole to mole ratio. 2 carbons to 4 hydrogens to 3 oxygens. Now I do want to find the molar mass of this, or the molecular formula of this compound, and I am given molar mass. In order to do that, I need to know the molar mass of my empirical formula. So if I add this up, the mass of this thing is 76.05 grams per mole. So for your molar mass calculation, I want you to take your molar mass and divide that by your empirical mass. It's going to give you the ratio of the molar mass to your empirical mass. So I've got 228.156 grams per mole divided by 76.052 grams per mole. This gives me 3. This means that my molecular formula is 3 times that of my empirical formula. So C6H12O9. This is my empirical formula. This is my molecular formula. Empirical formula for the stimulant based on the elemental mass percent composition, nicotine. Carbon has 74.03% composition in the sample. Hydrogen is 8.70% and nitrogen is 17.27%. So again, we are going to assume a 100 gram sample. Number of moles of carbon is 74.03 grams. Convert that to moles of carbon. Gives me 6.16 moles of carbon. Number of moles of hydrogen, 8.70 grams of hydrogen. Convert that to moles of hydrogen, 1.008 grams of hydrogen to 1 mole, and I find this to be 8.63 moles of hydrogen. Number of moles of nitrogen, 17.27 grams of nitrogen. Convert that to moles of nitrogen. (1.23 moles of nitrogen). Find the smallest number and divide all of them by the smallest number of moles because we want that mole to mole ratio. Smallest number is 1.23. So divide this by 1.23 moles. This gives me 5. Divide this by 1.23 moles. Gives me 7. And divide this by 1.23 moles. Gives me 1. The empirical formula here, C5, H7, N. A whey powder is analyzed and found to have empirical formula of P2O5. The compound has a molar mass of 283.88 grams per mole. What is the compound's molecular formula? P2O5. So remember, empirical formula is just your lowest whole number multiple ratio. Molecular formula is your actual formula. So your molecular formula will be a multiplet of your empirical formula. P2O5 has a molar mass of 141.94 grams per mole. If I know your molar mass is 283.88 grams per mole, divide that by your empirical formula, weight or mass, 141.94 grams per mole, and I get 2. That means my molecular formula is a multiplet of my empirical formula by a factor of 2, or P4O10. Let's practice some basic namings. Write the formula for the following compounds. So I'm giving you the name, I want the formula. Sodium nitrate. Sodium, alkali metal, group 1. Na, group 1 is always +1 charge. Nitrate, one of your polyatomics, NO3 minus. Cross your charges, and we get NaNO3. Aluminum hydroxide. Aluminum, Al, always 3+ charge, no exceptions. Hydroxide, polyatomic, OH minus. Cross our charges, and I see that I need 1 aluminum for every 3 hydroxides. Because I need 3 hydroxides, I have to use parentheses. AlOH3. If I wrote it without parentheses, it would look like this. This is not the same thing. Potassium bicarbonate. Potassium, K, group 1, alkali metal, always +1 charge. Bicarbonate. Well, carbonate is CO3 2 minus. If I see the word bi, that means I've added 1 H plus to it. So H plus and CO3 2 minus give me HCO3 minus. So bicarbonate is HCO3 minus. Cross my charges, and I see that I get KHCO3. Phosphorus disulfide. Phosphorus, P, sulfide. Remember, the I is just the anion ending. Sulf tells me the element, so sulfur, and di tells me I have 2 of them. So PS2. Nitrogen trioxide. Nitrogen, oxide, ide is for the ending, ox tells me it's oxygen, tri tells me I have 3. NO3. And lastly, sulfur, S, pentachloride. Ide is just the ending, tell me it's an anion. Chloro tells me chlorine. Penta tells me 5. SCl5. Number 17. A chemist decomposed the following sample. Determine the empirical formula of each. Again, I don't know why I have the word of each written there. Knock it off. Sorry. I'm trying to... My cat really likes to eat things she shouldn't, specifically plastic. And she's trying to be naughty. Okay, so back to class. Sorry, guys. I've got 1.651 grams of silver and 0.1224 grams of oxygen, and I want to know the empirical formula here. Number of moles of silver, 1.651 grams of silver. Convert that to moles of silver. Silver, 107.9 grams. This gives me 0.0153 moles of silver. Oxygen, number of moles of oxygen, 0.1224 grams of oxygen. 1 mole of oxygen to 16 grams of oxygen, 0.00765 grams of oxygen. Compare the two numbers and divide by the smaller of the two numbers. This is the smaller of the two numbers, so I'm going to divide them both by 0.00765. That should not say grams there, that should say moles there. For silver, this gives me 2. For oxygen, 1. That means the formula here, Ag2O. Now, this formula shouldn't surprise us, silver oxide, because we know silver has to be Ag+. We know oxygen has to be Ag2-. So therefore, it makes sense to me that Ag2O is the correct answer. You would still have to show work on a problem like this to get full credit, but you should be able to check yourself by understanding the naming. And last question. Identify if the compound is ionic or molecular. This is just, again, to help you remember naming. Magnesium, metal. Oxygen, nonmetal. Definitely ionic. By our definitions. Again, this is a spectrum, but by our definitions, we're going to call this ionic. Nickel, metal. Hydroxide, nonmetal, polyatomic, actually. Ionic. Ammonium, polyatomic. Chloride, nonmetal. Polyatomics have a full charge to them. This is going to behave as ionic. Nitrogen, nonmetal. Oxide for oxygen, nonmetal. This will be molecular. Phosphorus, nonmetal. Trichloride, standing for chloride, nonmetal, molecular.